Hello and welcome everyone to Knowledge Optimizer. I am Rajat and today we are going to start with another system design principle, that is scalability. So suppose you have built an e-commerce website for yourself. Okay, let's take an example. So you have built an e-commerce website. Okay, now you have launched your website in Jan on the new year. Okay, now your website work fine. I consider the case it is we are just selling clothes right now, the category. It could be men, women, and all those. And then from Jan to basically something around September, the traffic was somewhere like linear only, like the graph looks like this. Okay, this is user, this is month. But as the Diwali season came, you see a huge spike. Okay, and here there is a huge spike on your sale, but your system is not able to handle, basically your server or website is not able to handle that much load, and it went down. What do I mean by went down? Basically server start crashing. So yeah, I think you might have heard this news. Yeah, the Instagram or Facebook start crashing or it went down, basically nothing is working. So similarly on till from October till New Year, till December, there is this spike, and due to which but you are not able to serve any request due to your system went down. Now there is one thing called, you can instead of this crash down, basically this whole website going down, you have introduced a rate limiter. Okay, limitation on the number of requests your server can serve. So you have introduced some kind of rate limiter, like now due to this, so that at least whatever servers are present, at least those many requests can be served here. Okay, now 50% requests are able to be served, but we are like 50% of the requests are dropped. Now you can see a loss in business. Okay, this is a loss in business for you, and it would be not even just 50%, it will be huge than that. There could be number of users which were your regular users, those requests were the request for those users are dropped. So definitely don't want that. So basically you want to serve all those requests, so definitely rate limiter is not an solution for that. So then comes the scalability in picture. So what do I mean by scalability is basically the ability of the system to perform well in case of huge load, in case of huge user base. So that's called the scalability. Okay, now there are basically why scalability matters. Now moving to that. So you got scalability. Scalability is just a ability of a system to perform in case of huge load. How it is performing? It has to perform basically smoother. So that's called scalability. So there are few places where your scalability has to matter. Where it is required. Growing user base. Now what do I mean by that? So suppose you have launched your an edutech website. Now you see a linear growth. Okay, linear growth per time, user time. Now you have launched your website, now you have kept it same. So till this point everything start working fine, everything was working fine. But post that point, many of the requests start or you can say servers start crashing, or many of the requests were not able to serve. So here, from here, basically you need to see like how you can scale your system. Okay, like the current system which you are running, the number of pods, I'll say number of pods, what do you mean, number of servers you are running, those were able to serve the request till here. After this point you have to introduce more servers basically. Now moving to market demand, the last example, previous example which I took, Diwali sale or New Year sale, this is the that means this market demand only. What do I mean by that? There is sudden peak or spikes in the market demand, and then you have to increase your pods. Now many company perform different ways. Okay, I'll just show you through an AWS example also, like how this auto scaling been handled there. So what does happen is, like suppose you have, again we have launched a website. Now your website is running a number of pods. Now what people do is basically now they start using some cloud services. Okay. Before moving to this, okay, before moving to this, actually, consider the case. To handle such a load, let's forget about cloud services. We have to first of all understand why there was a need for cloud services, why all the companies have moved, basically max of the companies have moved to the cloud services. Okay, suppose now you have launched your website. Now you see like during Diwali sale there is a huge traffic. So what you have done is initially only you have purchased like 50 machines. Okay, 50 servers you have purchased, and you are running your servers, 50 machines. Okay, and you are running your website on all those 50 machines. But you see from Diwali, sorry, from Jan to September, the number of resources you are using are just 10%. Number of servers you are using just 10% of the total servers you have. Whereas during October to basically December, you are using 80%. Okay, total servers. So you can see there is a 90% of the resources are wasted during all those seasons. So there was no need for me to purchase 50 servers initially only. So that's where this now comes the cloud services. Now what does cloud service provide is basically on demand servers. There are two types of servers. One is on demand and one is provisioned. Okay, what do I mean by like ideal servers which would always be running? So there are two types of servers. Okay, on demand or ideal servers which would always be running. Okay, now what companies do, okay, so from Jan to, consider like I have running five ideal servers from Jan to September. Five ideal servers I was running. From October to December, as soon as you see a huge traffic, so basically it auto scales to 500. Okay, 500 servers. When it saw that huge spike, so it auto scaled to 500 servers. So this is how the most of the requests will going to be served. But again, there is one more scenario. So if you see during October, as soon as the Diwali sale, so they gave a specific time, like Diwali sale is start from this date. Why? So what they do on that specific, since these uptime of server uptime, it also take few seconds. Okay, like we can say 5 second, and server is taking. So for that 5 second, basically from 5 to 500. Now for those 5 second, you can say like there could be multiple 5 second for single server, like consider 5 second it takes. For those 5 seconds, the all the requests would be, so they are just, for all the requests they are just five ideal servers that would never be able to serve all the requests. So there would be a latency of these 5 seconds. So what people do is basically they give a specific time. What companies do, they give a specific time. Okay, Diwali sale start at 12 a.m. on this date. So before that date only, they basically increase their ideal servers to 50. 50 ideal servers would be running now, and now they can scale up to 500. So what they do, from Jan to Sep, they would run five ideal servers. Now, as soon as that particular date on which the Diwali sale started, they increase their server to 50, or you can take one number, higher number, and now it can scale up to. They can you can apply a limit also, like auto scaling limit, till what number it can scale up to. We are, consider the case we have applied it to 500 server. Now the servers can be scale up to 500, but at least we won't have this latency. Those 50 ideal servers would be able to serve those requests, serve that small peak which suddenly came. So that's the main funda behind it. Now growing user base, market demand, that's where scalability matters. Now Coming to, there is a cost efficiency also. Actually, it's the same example we will take what we had taken in the last slide, last page where we were talking about market demand. So, like you have purchased 50 machines to serve your request initially. Instead of running, I was talking about, like instead of running 5 servers, 5 machines, you were running 50 machines initially. Like, consider like there is no, we are not aware about scale auto scaling. Okay, so what people earlier used to do, basically bought 50 machines. Now 10% of the resources would only be used maximum of the time, whereas 80% during peak seasons. Okay, now this 90% of the resources are wastage. Whereas had I been going ahead with this scalability solution, then in that case I would just pay for what I am using. Then in that case, 80%, like the my they say 90% of the resources, so you can say 80% of the cost would be saved for me. So main fund of this is pay for what you are using. Pay for what you are using. So whenever you move to any organization, if you'll see, like initially we are keeping that number of pods at huge number, then there would always be this resource wastage. Then you just have to identify actually a balance, actual balance you have to identify. Like if there's a small peak, then in that case I don't have to go to this auto scaling. Basically, I don't have to keep more ideal servers. So the servers should be those limited amount only, okay, to save the resources also, and uh, basically for that purpose only. And it varies from companies to companies. Okay, what do I mean by that? Okay, when you are okay, consider the game, you are on Prime Videos. Now they have launched you'll say a movie which is very hit, kind of very popular movie. So suddenly when they start searching that movie, the video start crashing initially. So this won't, but it won't lose any business. It won't lose business. So they won't basically change their ideal servers. Before that, it will rely on auto scaling for time being. It won't increase their ideal server from 5 to 50. 5 ideal servers would only be sufficient. Okay, it won't. But whereas in case of e-commerce website, if you are not placed 50% of orders, then in that case you have to keep ideal servers to 50, and auto scaling should be enabled. Why else 50% of the orders, like in the small peaks, 50% of the orders won't be able to serve. So that's the difference. Like you have to identify what kind of business you are working in, and how to you have to identify basically the balance, how many posts to run, and how the scalability should perform. Okay, cost efficiency is one of them. Then future proofing. So currently, like we took the example of edutech only. So till this point, this is, you can say, failure point for a single machine you are running. You have deployed your e-commerce website on a single server. Now, after this point, basically the servers start crashing due to the huge load, not able to serve that load. Then in that case, basically keeping future perspective in mind, we have to keep like number of ideal servers to the number of basically auto scaling required or not. Scalability we have to kept in picture, because after a while everything will start crash if you don't scale your system. Okay, now this is very okay, now moving to next topic, that is types of scalability. Scalability is of two types: horizontal scaling and vertical scaling. Vertical scaling. Okay. What do you mean by, first of all, let's cover the vertical scaling. Like you have a single machine, okay, as well. Now, as soon as you see like this machine not able to serve the future requested, the more requests whenever you are going to, so you just increase the CPU and memory to a limitation, basically to a limit. You have increased it too high, so high power, cp high cpu, high storage. So you are using machine that way. Basically you are scaling a single machine up in a, but this vertical scaling, there is always a limitation till what point you can scale. Also, like you have used a high power machine, okay, now you have deployed your system again. Consider the case this system is able to perform, basically not able to serve all the requests, okay, whatever request you'll get. But that will only be happen in some cases, okay, for max of the time, like in the case of Diwali example only, till Jan to September, this system would only, basically this server would only be serving 10% of resources will only be using, it would only be using, okay. Now the 90% is still a failure. During these, consider the October to December, during these seasons 80% of the resources are used, okay. But this resource wastage is high in case of, though I don't need that huge machine at initial level only, but I'm keeping it. Though in case of this huge spike, usually single machine is never able to serve because there is always a limitation on cpu and storage. So these were the two factors due to which people start moving from vertical to horizontal scaling. What do I mean by that? Basically they would be now as soon as the traffic increases, you are going to introduce more machines, okay. So in the last example we take, we usually keep five ideal servers. That what I meant by that, basically there would be five servers running. Now they would be kept on SN, there could be 500 also, 500 machines running, okay, to serve multiple requests. And all the servers would deploy only a single, all the servers, yeah, will deploy e-commerce website only, my e-commerce website only, okay. Now this server can also receive my request, this server, but only a single at a time will receive my request, and they'll serve it. Now you can see, okay, this is good actually. Now you can see the cost, and cost would be low, as I'll just pay for what I'm using, pay for what I'm using, okay. So due to that cost is low. But as soon as you distributed all your servers, there comes, now you can see there could come the problem of partitioning. We will come to that later. What do I mean by that? Like which server will going to take which request, will going to serve which request. So there would be multiple scenarios also, like fault tolerance. Now how the load would be distributed, for that we use load balancers. So all those things we are going to cover later part in this video, okay. So these were the mainly two types of scalability: horizontal scaling and vertical scaling. Now let's move to the key principle, okay. Now key principle of scalability. So first is statelessness. Stateless. Now what do I mean by that? Is basically servers are unaware of previous interaction. Okay. Basically they are not caching anything on them, like what was the previous interaction about, what about, and all those things. So what do I mean by that? So consider like uh, this is a server S1, S2, not move to S3. This is a single server S1. Now request 1 came R1. Now request 2 came R2. This R2 won't have any context of, basically sorry, when this server R1 is going to serve this R2 request, then it won't have any context of basically what it served for R1 when it is serving any4 to R2. Basically, it is isolated. Both the requests are isolated for it. Okay, this is the main idea. Like server is unaware of any previous interactions. So you can say like it can store like user history and all those things how it is going to serve. So that would be passed on by the request only. That should be passed on by the request. Then that's what stateless means. So if server is unaware of previous interaction, then in that case I can basically create scale it to any system S2, S3, S4. Now R1 is served by this, R2 can be served for a single user only. Consider this is for user 1, then R2 is also for user 1 only. So R2 can be served by this, or R3 can be, or R4 can be served by this, irrespective, because since servers are unaware of previous interaction. Now people ask like if I'm logged into a system, how it is going to handle all those things. So what usually happen is whenever you are like suppose this is a request where it asks you to log into as you basically server, then in that case a user authentication token is generated. Now all the requests, future requests, R2 or R3 or R4 basically have to provide that user authentication token. Usually you have seen in your this REST calls that user authentic auth token kind of thing. Okay, so those will provide by the request only. Now request and it can be stored in browser cache. Okay, cookies. So there we store all these information now, and whenever you are going to make any request there, so these are from these cookies and browser cache. Basically you are going to append those things in your request. Now request will going to pass all those information to servers. Now since you have logged into the server, when you will go with authentication token with on this server, now it will just validate that auth token. It won't ask you to basically log in again to their system if you go there on server 2, though you have logged into server 1, but it will passed something like auth token and stored it in your browser cache or cookies. Now all those future requests, further requests which are going to be make on that website, whether it is server S2, S3, S or S4, now you will get those information, user credentials or user information in that request only, so that you don't again have to log into the system. If you disable your browser cache, then again you have to, if you have logged into this server, then you again have to log into this server. If you are disabled, if you don't, if you are not passing all those things, all those headers, all those information in the headers, then in that case you have to again log into this system. And if your request being served R3 be served by, then again you have to log into this system. So that's the main idea. You can see like how scalability got easier in case of statelessness system. Now there is opposite of it is stateful. What does stateful meant by it? It basically kept information about previous interaction. Now there is a session storage. Now S1, it will store a user session on the server S1. Now now and there are other information also being stored on the server side. Like earlier this was the this was what used to happen. Basically most of the things being used to be stored on this server side. Okay, so but you can see if I go ahead with this stateful system, now if I scale it to S3, S4, now request 1 came to this. Okay, like earlier nothing was there. Now request 1 came to this, user logged into this server. Okay, now the sessions information is stored here. Then in that case, if R2 request 2 of user 1 only, if it doesn't came to this or basically came to this server, then in that case this server again ask the user to log in to their system, right? If further R3 call comes, then this server will again ask the user to log into this system. So this is the scalability problem in stateful system. So there are some solutions like shared session. There are ways to implement it. Shared session, like distributed cache. Basically, cache you can using. So there would be a central cache now. Okay, central cache. Now what will happen? This instead of using those information here, user specific information, you are going to store in a cache. Now S2 will also be fetched from cache. S3 also fetch that session information from cache. Okay, caching is a way. There are these terms, shared session or sticky session, you might have heard. So these are the few ways you can achieve scalability in stateful system also. But it is recommended to go with statelessness system only because you can see that multiple problems here. Okay. Now you can ask me where to use what stateful. So can you give me more, if I give you more simple example. So if you have gone to any e-commerce website, even without login to that website, you can able to serve, you can actually search anything. Okay, like if I go to Amazon, then I am able to search anything. Okay, and Amazon without even logging into it there. But as soon as, so this is an example of statelessness system. You are able to search anything without even login, without any information being stored there. This is a basic, very basic example of statelessness. Whereas when you have to add item to cart, then in that case you require stateful system. What do I mean by that? Suppose you have added any item to cart 1. Okay, now here, and it is being served by S1. Now if you are adding another item, okay, another item in the cart, then that case, if it is being served by this S2, then in that case you will see cart is empty. You are adding first item, though there were some items you had added at server 1, so where they are missing. So that's where stateful system come. Basically you have to maintain the previous interaction. So all the requests now, all add items are add item to cart should be served by this S1 server only. So there's this load balancer comes into picture. They basically, okay, this they'll create a basically some kind of hash for a particular users. Now for this particular user U1, all the requests will be served by S1. Okay, but the problem with it is, okay, we'll discuss when we'll talk about load balancer. Okay, we'll discuss this. Okay, uh, I'll just give you a problem with this is, since suppose all the high resource tasks being done by user 1, then in that case you'll end up increasing load on a server 1, whereas S2 and S3 being sitting ideal, though they could have served some requests, but they are sitting ideal. So there is another way also, like instead of implementing it this add item to cart, you can just implement it through a statelessness system. So what you'll do is, basically whenever user any item to cart, you start interacting that with database. Now you'll fetch from database. Okay, uh, sorry. So like some items are already added by this user in the database. Okay, in the cart kind of. And now it will fetch and it will show the data whatever added in the cart, and it will just further update whenever any update being done on the cart from there or there or there. It can implement in the both ways, stateful or stateless. So that's the main idea behind it. So obviously it is easier to scale this, and you have to keep the system statelessness only. You have to go ahead with statelessness when you are dealing with the scalability. Now coming the another key principle is loose coupling. Now coming to loose coupling. Okay, so suppose you are building a monolith. So suppose you have starting with a monolith. So there is this user service, there is this product service. Okay, product service, then there is this user service. So you can see clearly see like there is a huge traffic on user service, cause many of the times many of the users will basically, actually it should be opposite. There would be a huge traffic on this product service, like many of the users will just be searching for the product without actually logging to your system, but there is a less load on user service. But since there is a huge load on this product service, you will just increase the pods of this. But these resources, though there was no need for scaling this system for increasing resources for this user service, But since you have kept it in such a way, you have implemented a monolith, that your resources, those resources where you are since you are just scaling this whole system, though there was no required for user service, just wasting your resources. So that's why, like, you can separate out this product service, then user service. Now you can scale it to 50 pods, where this is running on 5 pods only. So that way you can just save your this cost. Okay, this is the main funda behind this loose coupling or moving to microservice architecture. Now comes replication. So this is again an interesting thing. Okay, replication. Let's see from the top level only. We won't go from users. Basically, let's start with this. So you have this system. Okay, user service or product service P1, product P1, and this is running on n pods. Okay, one, two. Product service is running on n pods. Okay. Now since the database is same, so this also, and dot 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 this also fetching from this database all the information, all the product information what to show. Okay. So you can see a bottleneck here. What do I mean by bottleneck? Basically all the requests are serving. Whenever you see any such, whenever you are giving any HLD interview or designing any HLD problem, so whenever you see a structure like this, everything, all the arrows coming to a single block, then you can say like that block is actually a bottleneck for you, and you have to do something to mitigate that. Okay, here in our case database is a bottleneck, so you can see like multiple arrows coming here. Basically multiple requests are being, since you have scaled your these services. Okay, but you are using a single database. Okay, so obviously this is a bottleneck, okay, for you. Now how to mitigate it, that's the question, that's the main idea behind replication. So usually what people do is go ahead with two structure, master slave. You might have heard of if you have read any where application. Then master master. What do I mean by master slave? First of all, master means it can perform both write and read, and slave means it can only perform read operations. So what people do is basically this. There would be one, first of all, in the master slave structure. So there would be one master and multiple slaves, S1, S2, S3. So this is a master slave structure. Now all the, since read is usually 80% to 20% ratio is always there, 20%. 80% read, 20% write. Like you would be searching for 80% of the product, but just adding 20, basically 20% times you were just adding. 8 times you, out of 10, 8 times you will be searching the product, 2 times you will be adding that to the that cart, kind of. So this is the usual trade-off. Then what master slave do is those 20% requests, these 20%, all the write will be served from here, and all the reads would be done from these replicas. Okay, and these can be updated, these slaves can be updated asynchronously. Okay, or some mechanism you have kept, like some cron or some triggers. Basically these are updated asynchronously, but all the writes will happen on master, and all the reads would perform from this slave. Now there's this, just in master just opposite, like there would be, since this is also master, this is also m2, this is m3, all three are master, all the writes and read could be happen here. Write and read, all the write and read can happen from here. Basically you have created a replication, replicas of it, write and read. Suppose r1 basically w1 is the write request, w2 is a write request, w3 is a write request. Now r3 read 3, basically r3, r2, or R1 being served from here, and also asynchronously we have to kept them in sync. Now you can see this update, this basically these arrow where we are updating from one writer to slaves, or you can see from writing from on this but replicating same, basically updating other two here. So there would be some latency. Okay, yes, obviously there would be some latency. Then comes, like, but how you are going to serve if there is a latency? Then comes another uh, another good topic, that is cap theorem. Okay, so what it state, first of all, C stand for consistency, A for availability, then P for partition. So what it states is basically at a single time you can achieve two out of three, these three, two out of three. So in case of network partition, so suppose these are the three pieces of a tree, or you can say of a triangle. Then at the same time, like, this is the simplest, like there is no partition. No partition means there is a single machine running, single machine, you can say. In our case, let's take the example of database, single database running, and consistency and availability both be there. What do I mean by consistency? Like, all the data being served from all the replicas would be same data. Basically you'll get the latest updated or latest updated data. You will either get the latest updated data or error. That's the main idea of consistency. Availability, you'll get some data. You will never get an error, you'll get some data. It could be, it cannot guarantee that it would be a latest, it could be latest or could not be, but you cannot guarantee it. What do I mean by partition? Like, okay, this is simple, just a number of pods you are increasing. Like, there is a partition you are creating. It be in our case, it's master slave like kind of partition we have created. Okay, some partition we have created. Now, since there is a single machine or single master, you can say single instance of our database is running, then in that case, since there is no partition, there is always be availability and always be consistency. Since there is a single, you can say, machine running, obviously all the requests being written on this only, and all the requests being read from here only. Okay, now consider the case there are partitions. Okay, this is partition 1, partition 2, partition 3, p1, p2, p3. Now there are two trade-off since partition is done. Okay, now either you can achieve consistency or availability. What do I mean by that? Either if you update something, this is a master. If you update something, sorry about that, if you update something here, okay, now whenever, so consider the case, request, basically the replication doesn't happen here till now. All the data are not updated on these replicas, data yet not updated. Okay, this latest information yet not updated. Then in that case, when you are going to make any request, and if it is serving those requests, it is giving response, it means your system is following these trade-off, availability and partition. If it gave you any error, like consider another case. Now, till now, these are the replicas. Till now, basically not able to sync the data in these two. This is master, these are slave, and till now the data being not synced to these slaves. And if you'll make any call here, and basically it gives you error response. So that means you have achieved CP, here CP, here AP, availability and partition, here consistency and partition. Okay, else it will respond. If it is being replicated everywhere, kind of synced everywhere, then in that case it will provide latest response, and it will provide error response. So that's the main idea of this cap theorem. Okay, Now, where to use what? Basically, in industry, whenever, so they are like, when you cannot achieve 100, you cannot work on 100% consistency or 100% availability system, obviously. So there is usually a balance like 60% availability, 40% consistency. But in case of like you are, so this work fine with e-commerce website, but you are using with dealing with the stock website, then in that case it should be 100% consistency only, else there would be there would be many legal cases on your website. Okay, so that's the idea behind this gap theorem. Okay, now let's move to, okay, so there are two small principle also, caching. So caching is a way where you can decrease the load on your servers. Basically, it's also like 80% of the requests, since 20 80% of the request came from 20% of the users. Usually 80% of the traffic on your website will always be from 20% of the users. So keeping this in mind, so 80% of the requests are usually served from cache if you have implemented in a such a way, kind of. So that basically decrease load on your server. So there would be uh, obviously there would be less processing on the server, and you are able to serve those requests very fastly. Now coming to one more key principle of scalability, that is async processing. What do I mean by that, asynchronously? Basically what we do is, so suppose, okay, I'll explain the same through an example. So actually in my last organization I was working on a feature called video feed. So we basically was building a personalized feed for some users. Okay, not some, actually for all the users we are kind of making personalized feeds, kind of Instagram only. Okay, so but now the problem which we faced, so what used to happen are, the feed which we used to derive, those were based on some user attributes, and then some uh, global attributes. Okay, now when a user came here, okay, whenever user used to land on this feed page, so we used to get all the user attributes. So those were across multiple databases. So there were very like there were multiple microservices. Now for fetching all the user attributes, we first of all, like suppose some user purchased some product, so we used to go to that system basically from where they have purchased. Similarly, if it has opt for some booking, then we used to check like what booking it has for asked for. So they were like basically many user attributes we used to fetch from different databases. So for that purpose we start using big queries. Okay, and similarly there were some global attributes we had created for optimization purpose. We have created a consolidated table. Okay, now for this, basically for user attributes, they were like big queries we start using Trino or Athena kind of basically those databases for our this purpose. But the query time complexity was very high. Basically, it used to take few seconds. Now, the problem is you cannot make the user wait for few seconds to load their feed. Nor you can show a static content here, right? Like same feed for all the users. You cannot do that. So then we came across a solution, kind of async processing. What we used to do, there used to be a cron running. Since the user attributes doesn't change that frequently, or the attributes basically, so we used to have a cron running, and on this cron, what this used to do, basically on the basis of different attributes, it basically used to generate some feed common attributes. Now what we used to do, when user used to land on this page, since we already have generated the feed on the attributes, we just had one thing to do now, just consolidate them on the basis of some scores, like how much to take from which, and thus we only have to do merging part of it. Okay, so that's how we achieved that, though it was also not scalable. And later, like we have moved basically I can, if you want, I can start a series on that. Like if you want to build an OTT search, how you can do that. So how elastic search is used and all those things I can build if you want. So till now, I was just trying to show you, if your query takes, basically if your API is taking few seconds, then in that case you have to basically run those processes in asynchronous manner which are not required. Like if you have to trigger some event for some other service, then in that case you can keep that in async manner. You don't have to wait for that network call to process. Okay, definitely you can keep them in async manner. Whatever has to be performed by this API, it has to be specific to that. All the other component which is increasing the latency, which are not required by this API, then in that case you can keep them in async run them in async fashion. That's the main idea behind this. So these are the all key principle of this scalability. Now coming to, I think, scalable architectures we can discuss, though most of them we have already discussed, but I'll still them. So what are the few scalable architectures? Okay, here only. So here only we'll also cover that load balancing. I think last time we discussed. So first of all, microservice. So I think so far you already know the advantage of microservice. So basically you can scale one service, one microservice, M1, M2. Also you can basically separate out the load, like DB1 you are using for this DB2 has you been single monolith, then in that case the load would be very high on a single database. Here you can just scale this, suddenly you can scale this, and if you don't want to scale this. So that's the main funda of microservice architecture. Why it is beneficial for a scalability. You can scale single microservice, single database when it is not required to scale the other microservice, so that the cost and the resources can be saved. Similarly, this event driven architecture. So I have talked about this basically in the last page only. Basically, we discuss about we have to keep things in async fashion. So that's the main idea behind this event driven also. So what it say, like whatever doesn't has to be real time. So this is a actually this is one of the important part when you are giving any HLD, designing any HLD or giving any HLD interview. This is the most important part, like when to use event driven, when the thing is not real time and you can run it at any time with a some latency, then that case go ahead with event driven with the eyes closed. Okay, that's the main advantage. Since it doesn't has to be real time, it won't impact basically this it doesn't has to be real time. The load would be, we can distribute the load in such a manner, like we can process them later also. So if you have seen SQS, if anyone has worked with SQS or Kafka, those are the example of it. Now the load is distributed, like though there could be a large storage we can keep, like millions message can reside in this SQS. But since it's not hitting you on your server on real time basis, so then in that case this load cannot impact much on your server. Okay, though you have to process all those messages, but you can process them later also. There can be some delay, but delay is accepted in case of event driven. So that's when we use event driven system, and this is also important. Allow also, okay, I'll come to that later. Now actually whenever you are building any HLD diagram, no, these go together kind of, starting with event driven, then which microservice will consume what. Basically these are kind of independent, you can say. Cannot build a system from one architecture to be serious. No system is ideal enough. Similarly, you can, like I explained you the same in the cap theorem, it cannot be like 100% consistency, 100% availability. There is always a trade-off. There is always that small component you have to 80-20, it can be 70-30, it can be. Similarly, when you are dealing with real-time event driven, no system can be completely event driven. Similarly, no system can be completely real-time. So that balancing you have to identify. Okay. Now the next is this load balancing. Okay. Actually, I'll separate one for that. Load balancer. What are load balancer? Okay. So suppose you are working on a system, you are a user. Okay, you are user this. Now there are like n users. Okay, okay. Consider like there is a single server for so far. Okay, you are running, you are requesting on this server. It is S1 is working fine till the load is fine, okay, but as soon as the load start high, it basically start auto scaling themselves, S2, then S3, then so on. Now this traffic will be distributed. Earlier it was hitting on the single server, so it was easy to manage. Now in that case, now how you are going to basically, how you want all the traffic to be distributed, then comes this load balancer in picture. So it resides between user and basically the server you are hitting on. So there would be a load balancer, LB, then there are server, S1, S2, S3. Okay. Now these loader balancer will hit this and it will basically distribute all the requested. Now which request to go where, that is decided by load balancer. So the basic you can think of, load balancer will do round robin. Okay, what it will do, it will just first request will go here, second go, third go here, then fourth, fifth, sixth. Now consider there could be a chances like all the requests reaching on server 1 are of high resource consumption. Then in that case will basically this will be maximum time it will be occupied and they would be sitting ideal, though they can perform some of the task of it, but they won't since the request haven't came to them. So the load balancer is implemented in such a way to avoid these scenarios. Like similarly, if it is required, like I told you the case of cart. If you are adding item to cart, then all the requests for a particular user should go here. Stateful, in the case of stateful error, that also load balancer can take the responsibility. Like it can create some kind of hash for some users. Okay, so these are users. Now user will create a similar kind of hash and all the requests with this hash will go to this server. Though again the scenario can be possible like maximum load will be on one server. Okay, so that's the main functionality of load balancer, is to manage the traffic in such a way basically all the servers are like all the traffic would be distributed among them. No, not single server is impacted on that. Now coming to, so I told you, I think when I made this figure, there's one picture you can see here, you can see a bottleneck. Obviously I told you whenever you see those arrow coming on a single point, then it's a single point of failure, single point of failure, or called bottleneck. Okay, so to avoid bottleneck, there could be many multiple load balancer. I won't go in detail like how to distribute them. I think I already gave you an example of the database replication. On the similar terms, you can think like what are the different strategies can be like there could be one main this master load balancer can be there, while other would be just replicating its property, or there could be two masters. Zookeeper, usually you can read more about Zookeeper. Zookeeper is a tool to manage kind of all these things, all these distributed load balancer, or whenever you are dealing in some kind of these distributed distributed system. In that case, Zookeeper is a kind of management tool you can think of, managing like when to suppose this load balancer go down, then Zookeeper make sure like this make it master. Earlier it was slave, but it will turn that into master and start spawn a new load balancer, the same configuration. Till then, so there is a, I don't remember the exact configuration. It is some like more than half, like sorry, nearly half of the these you can say servers. Nearly half of the servers are down. Then in that case, we can consider it to be a system to be a down. Half pod, more than half pods are down, or nearly half pods are down. Then you can consider that to be a down. Now moving to another principle, that is sharding. So sharding is an interesting topic again. So I have told you database replication. Okay, told you about database replication. But now there is a scenario of database partitioning also, or sharding you can say. So what we usually do, suppose there are 1 to n, okay, 1 to n number of rows are there in your database. Now what you do is basically you create a partitions of it. Now 1 to 1000 are in this partition, 10k 10k to 20k are in different partitions, so on up to something to n. Okay, these are in different partition. So this is called, so I think I meant, okay, we have talked about partition or sharding. So this is called database sharding. So sharding is a concept. Now whenever request came, now in which port basically it has to hit, in on which partition it has to hit, that it is decided. Again, you can create a some kind of load balancer tool, or to give you an example, if you have worked with the b plus trees, okay, so we usually keep a range tree. Now this range tree like 1 to k. Now they are further partition, okay, whatever this is 1 to k. Now whatever numbers I suppose searching for 1000. Now 1 to 1000, or 1 to k by 2 are stored here, k by 2 to k are stored here. Consider k to be 10,000. Now it will go in this direction. Now there would be further two partition, just keeping a two node basically binary kind of b plus tree I'm considering here. Okay, now further there would be one range, this 20k to something here, 1 to 20k here. Now it will further go here. So you got the basic idea. Like in b plus tree, what it is kind of range tree. I'll go in the direction where the my answer lies. Now at the leaf node, I'll basically try to hit that partition only. Okay, now I know on the leaf node, I'll know like this is the partition on which I have to look. Now I'll hit on the that partition here, this partition, get that value. So this is a, I'm just telling you, this is a one of the way to basically search in case of sharding. Now these are the some architectures in scalability. Now let's see some a few examples of scalability. Okay, so you might have seen Netflix. So again, it uses AWS for achieving scalability, auto scaling. Okay, it has to do many video processing tasks. Now also for traffic management, basically user and those information. So it uses AWS for that. Even for elastic caching, it uses AWS for that. Similarly in Uber, the database, the I'll say the users, it has to be, there are millions of real time writes they have to perform, and real time data updates. So they perform sharding on graph database kind of. Okay, they use graph database first of all. Then sharding is very easy in case of if you are using NoSQL database. Okay, I think I haven't covered that. So since from the partition you can easy, in case of SQL there is a relation, okay, relation we have to maintain. In case of whenever there comes the fund of relation, now it would be hard, like this table is related to some attribute would be mapping here, or some attribute would be mapping here. So if you can shard, you cannot shard some of the data. Okay, that is going to very critical, very difficult. Now whereas in case of NoSQL you just maintain a single table. You can consider the case of Dynamo, or this is that is a column database, or Mongo. Now there is a single table, there is a single index, basically fetching all the values in the JSON format. Now it is, you just shard from here, basically partition from here. Here partitioning is very high because there is a relationship maintained. Now if you store some of the data, you just partition it. Now you have to make sure that some of the data partition here. But if it is used here, like in this partition also this information is used here, then it is typical, replication is going to be very high. So that's why sharding is very easy in case of NoSQL. So these are, I think, many of most of the, actually all of the organization, whether it's Amazon, it's through Netflix, Uber, everyone where there is a huge traffic, like these are all the principal functionalities comes into picture and being used there. So these are, I think this is all from the point of scalability. Now we can see some of the challenges, or you can see disadvantages. Again, uh, since we have done the partition, the complexity is going to be very high. Okay, like earlier we used to have just a single vertical. In case of vertical scaling, we used to have just a single service which manage all the load. Now we have created partition. Like I told you, there is a problem of cap theorem. Okay, you have to keep a balance in between those two also. So complexity is increased with that. Now data consistency, again cap theorem only, data consistency is a critical. Like in case of you are dealing with a stock exchange, stock, not a stock exchange, yeah, actually stock market, some website is there like grow or somewhere. This consistency has to be, data consistency has to be high. Then the cost is also high. Okay, now, okay, if you compare it with this, then the cost is definitely you are saving some resources, but at the same time you are creating multiple databases. Okay, now the cost for them will be earlier we usually maintain this d1 only. We used to basically drop down some of the, we used to implement rate limiter, drop down some of the requests. So we have increased some cost, but it is actually beneficial for us only. Now the latency, in case of like I told you real time, the update is not real time, asynchronously, then there would be definitely a latency. Similarly, in case of like it takes some time, in case of auto scaling management, it takes some time to start a pod. Okay, so it takes some, so latency is there too. So these are the few things, but I think these are on the advantage disadvantage, what is the scalability. So coming to, definitely scalability is very useful, and and it is actually must to be there in your system if you want, if you are expecting a huge load on your service. If not, then in that case you can go ahead with that, but I think then it means, it just means if you are not making your system scalable, your business is not going, you are just wasting your money on your business. So that's all from this video. Let me know if you have any questions or anything in the comment section. Thank you all.